So good morning. As Dirk said, I'm Jean-Pierre Rosen from a company called Edalog, which is a company doing mostly his business with Ada. So you may think, oh, that guy will tell you how nice Ada is because that's his business. So let's be clear. In a previous life, I was teaching in an engineering school, compilation languages and so on, and I thought Ada was a good language, and I made my business on Ada because I thought it was my business. So it's Ada that drove me to having business with it, not the other way around, okay? And of course I have about 45 minutes, so I won't tell you everything about Ada. I just try to give you an overview of the spirit of the language and how it's different from other languages. Okay, there are some things, it looks like a regular language with usual feature, but as you dig into it, you'll see that it's more different than one may think first. So, the name Ada is not an acronym. It comes from Ada Byron, who is supposed to be the first programmer. So she wrote a program for the Babbage machine. I don't know if you heard about that. She could never run her programs because the machine was never built, but her programs have been rewritten in PL1 later, and they are said to have worked right from the start. So the first programmer was a lady, and the first program had no bugs. Things have changed on both these aspects. The first version of the language has been issued in 1983. So it was quite advanced for its time, with advanced feature like exception, generics, and tasking. There was, and there still are, no new features, no things invented especially for Ada. It's rather gathering together the best ideas from other languages. So everything you have in Ada existed in previous languages. It's just a synthesis of the best ideas that appeared in various languages. Due to the evolution of software, of hardware also, there was a major improvement in 1995 with the introduction of object-oriented programming, protected objects, which are a mechanism for synchronizing between tasks. Tasks is our term for threads, actually. In 1983, that was the common name for those things. It's later that the term threads was coined. And hierarchical libraries, which is a way to organize modules. Note that Ada was the first standardized object-oriented languages in 1995. The second one was C++ 3 years later. Then languages evolved. Well, you know that you always have different versions. And in 2005, the main addition was interfaces like Java or C# interfaces, and built upon, improved in general existing features. But it was less of a big bang as happened in 1995, and the story goes on. We had a new version in 2012, and it's going more and more formal, more towards program proofs. So we have invariant, precondition, postcondition, and things to make compiler able to prove behavior and more sophisticated checks at runtime. And regarding this evolution, I would stress that we went from a big bang in 1995, where it was a big rewrite of the whole standard, to a more continuous evolution where we gradually add more libraries and evolve features and less complete changes. So it's, in a sense, a sign of maturity. So we are in a free software event here, and it's important to note that free software does not like to depend on proprietary technologies. Ada belongs to nobody, okay? It's an international standard. There is no big pocket that owns it, which is a problem because we have nobody to pay for advertisements. Okay, so we're happy to be here to get the word through because it's hard because nobody has the money to pay for big advertisements. So we have free compilers. Well, first, so it's an international standard, and the standard is freely available. The standard has been published by Springer. Springer is not exactly in the free anything business. However, here is an excerpt from the copyright from a Springer book that says that this document may be copied in whole or in part. I guess that's the only book at Springer with that kind of copyright. Okay? The whole Ada effort has always been completely open. The standard can be downloaded in HTML, in PDF, in every form you need it. You have free compilers and proprietary compilers, why not? And many free resources. So here are some pointers, and you can type Ada something on the net, and you certainly find anything you need. Also a community with so news groups. The first one is in English, the second one in French, and there is one in Danish, I think. No? Jacob is not here. Okay. And, oh, where are you? I didn't see. Don't we have a Danish one?
No. We have a wiki in English.
Okay.
No.
Okay. And, well, the various channels, you know. We don't hear much of Ada, so who is using Ada? Actually, many people are using Ada, and you don't always know that you are running on Ada. For example, if you take a TGV, all the mechanisms that control the speed of the train, the needles and all the safety part of it are written in Ada. There is lots of Ada in the A380 and also in the A400M. This is the automated subway in Paris, line 14 and now line 1. They're running on Ada. And this is Rosetta, okay? 14 years in space, woke up and worked perfectly as expected, fully in Ada. And this is a luxury yacht, the King Cat, also fully written in Ada. When you buy that kind of baby, you don't want to be stuck in the middle of the ocean due to a software bug, okay? So why would you use Ada? First of all, we say when failure is not an option. There is a huge stress on writing safe and secure software. And that's why most of the examples were, I showed you, were safety critical. However, other systems should not fail either. And in a sense, I claim that Ada should be used more in non-safety critical systems. When you build a safety critical system, you have plenty of money to check everything. So even if you write in a crazy language, you'll have the money to make sure that it works. Now, if you are not in that business, you don't have that money. So it's important to have tools that will ensure you the same level of quality as required for safety critical systems, without having to pay the price, of course. So some buffer overflows are impossible here, okay? We have a way to dimension the size of a buffer according to what will be put in it. So it's impossible to have an overflow. All arithmetic overflows and all that stuff is checked, so they're all impossible. And many of these things can be checked at compile time. I'll give you an example in a talk, a small talk in about 12, if you're interested in that. But very often, something doesn't compile, and you realize that it doesn't compile because your design is inconsistent. The language is close to the design. If the design is wrong, it won't compile. So that's difficult to measure, of course, but that's a very interesting effect of using ADA. ADA is not just translating something into machine code. ADA is about checking and ensuring that everything's consistent. So, the idea is that what's important in a language is not what it allows. All people tell you, my language can do this and this and this. We are the only ones to say you, the language prevents you from doing things, from doing bad things. So what's important is what it forbids, not what it allows. So for free software, generally we need a consistent language. Here is a small picture. On the basis, you have a classical procedural language. The syntax is based on Pascal. There were requirements, and one main requirement was that the language has to be readable. And on the point of view of readability, the Pascal basis is likely to be the best starting point. With a very strong typing system, but truly very strong. Many languages claim to be very strongly typed, but here the typing system is really the backbone of all the language. I'll give you examples. With specialized features, packages to make clean, proper modules that separate specification from implementation. Strange enough, most languages nowadays don't have a clear notion of module. A class is something that's too small to represent a module. Often you need sets of classes that work together and so on. And that's something you don't have a syntactic structure for that in most languages. That's the package. Exceptions, now they are quite common in programming languages for handling anything that can happen at runtime. In ADA, anything bad is translated into an exception. Okay? Generics for reuse, something like templates if you want. I'll go over that. Multitasking is built into the language. Now you have Java, C#, a certain number of languages have built-in multitasking, but that was quite new when ADA started. And a bridge to low-level programming. I'll show you an example of that also, how you can have access to low-level features while still being in a high-level view of what you are doing. And all of this is intended to serve programming methodologies. That's very important. Nowadays, many people, everybody will tell you, well, what's important is to have good methodologies. Nobody will dare saying the opposite, of course. And people say, well, if you have a good method, then who cares what the programming language when it comes to coding? In ADA, we say no. There is no reason to stop the methodological effort when you turn into the coding phase. The coding phase should continue the methodological effort. The coding phase should translate the object of the methods, and the connection between the code and the objects of the method should be very clear. So don't give up the methodological aspects when you come to coding. including, of course, at least since 1995, our object-oriented methodology. Then you have some little dog houses here. These are the specialized annex. It's just, no, I shouldn't say extensions. They are complements to the language for very specialized features. They are optional because not everybody needs the same thing. So this is, for example, some extra packages for real time, or for high criticality systems, or for business systems distributed and so on. So that's just a set of specialized, I'd say, complements. So all of this looks like a classical language, but I told you it's more different than it seems at first view. Another thing that's special to Ada is the building block approach. We'll see. There is no syntactic construct called a class in Ada. Why? Because the approach is to provide reusable stuff that you assemble to build what you need. The idea is, well, you know the difference between Playmobil and Lego. Okay? Playmobil allow you have very nice pieces, very specialized. If you take a box, there is nothing from a box you can use to play with a completely different box, because they are all specialized, very nice for one purpose. You can't do anything else with them. The Lego approach is to have building blocks. What can you do with one block? Nothing. It's not interesting. Nobody plays with one Lego block, okay? But when you assemble them, then you can build very simple things like that, or very sophisticated like that, or even this. So the Ada approach is definitely the Lego. Okay, we have building blocks. When you put the blocks together, you build a class. When you put the blocks somewhat differently, you build something else. So the statements look like what you have in most languages, with a certain number of security features. For example, in a for loop, and note that every statement is ended by and you repeat the keyword. That makes it a lot more readable and helps you to understand what's happening. The C here that controls the loop, for the rules of the language, it's a constant, so you cannot change it. And it's a local constant to the loop, so it doesn't exist when you exit the loop. So you cannot cheat, you cannot change it in the middle of the loop, you cannot access it once you have exited the loop. When you see that, it is formally provable that C will take all values from the type color. Okay, and nobody will cheat that. You have a while loop, you can have named loops that allow you to exit the loop on certain conditions. So the power of expression of Ada is quite good. By the way, since we are talking free software here, remember, readability is important. The principle of free software is many eyeballs. The software should be readable by anybody. Okay? So having a readable language is something important for free software. So this is an example. I think you can understand this one. It is important to note that in the case statement is like the C switch, if you want. But here, given that we are strongly typed, we know the type of I, and the type is a set of values. Therefore, the compiler knows the set of values and will check that every possible value is given here in the when clause in the various branches. If you omit the when others, that the else or the otherwise, if you want, then the compiler will check the full coverage. And it's a very nice feature, because if you change the type of I, the first time you recompile, every place where you forgot to change your code, it will not compile anymore. So you say, oh, thank you, nice compiler, you tell me where I forgot to do something, rather than having the value simply ignored and you're chasing bugs for hours. Also, structured types have values like any other type, and therefore it's important to express them. So we have syntax, for example, to express directly arrays and matrices. That's how you can write a unit matrix in Ada. From the point of view of readability, then that isn't bad. Or here I'm creating a small linked list. So you see a new node whose value is 10,000, and next is a new node whose value is 209, and next is null, and so on. So the idea is to describe globally the structures and not to always return to the deepest level and the individual machine words. That's the idea. You try to work globally. So what about strong typing? Here I first define a type called an age, the age of a person, for example. So the lower bound is clearly 0. The upper bound, well, we can discuss it, but 125 should be enough. Or the floors in a building go to -5 with some parking floors to 15. These are conceptually completely different. So you can declare a variable of those types, assign correct value to them, but if you try to write my age equal my floor, the compiler will tell you no, this is of type floor, this is of type age, this assignment is not allowed. It seems so obvious, I mean, that you cannot add apples and oranges. But as far as I know, Ada is the only language that allows you to declare numerical types that are incompatible, so you preserve that different thing. It's not because they are represented by numbers that it's the same thing. Okay? The idea actually is that if you design something, you have a problem level where you define things that are completely different, independent, like an age, a floor, etc. You have a machine level. Machines deal with bytes, int, float, whatever. These are machine types. In a good design, what you have to do is first to analyze your problem and then make the translation into machine types. With other languages, the types that are provided by the language are machine types. Therefore, you have to do the mapping between the high-level problem-level type and the machine type. What's new in Ada is that you describe your problem at the problem level, and the compiler is in charge of doing the mapping. So a client tells you, oh, I have something that goes to 0 to 250, fine. Oh no, it was not 250, it was 260. No problem, I changed 250 to 260, and this will not break anything in my program. Behind the scene, all your types will move from 1 to 2 bytes. But that's done by the compiler. There are dependency rules that ensure that everything that needs to be recompiled will be recompiled, so it's not a problem yet. So packages are the way to control visibility. In general, you have what you expect to tell your client. If you want, it's an approach where you have a provider of a software component and a user. So you have the user view, which is abstract, and you can define a type as private, meaning, okay, there is a type, I don't tell you what it is. I keep it for me. And in the private part there, you'll have to give the full definition and maybe constants for, here I have declared constant, but I cannot give the value because the type is private. So in the private part, then you tell to the compiler, because the compiler needs to know what the actual definitions are. So you have a completely abstract view where you don't know how it is represented in machine, and then you define the representation. Oops. And then you have a body, and in the body of the package you'll have, of course, to provide all the bodies, the implementation of what you have announced in the specification. So in a sense it works a bit like a .h and a .c file. But there is no guarantee that, that you use a .h, just a convenience having includes in C. Nothing forces you to have inconsistent headers or whatever. Okay, here everything's checked by a compiler. And then you can use them. Here I have redefined operation like multiply and divide on colors by a real factor, and so I can use them normally. So the idea is to enforce abstraction in the sense that types that reflect the problem domain independently of the implementation. And also, when you use a package or anything else, by the way, you have to name it in a with clause. This means that whenever a module depends on another module, this dependency is always explicit, written in the source file. So it's very easy in an ADA program to know what depends on what. If I change that modules, which modules will be impacted and so on, you just have to follow a very simple graph. Something also that I know of in no other language is the idea of discriminated types. In a sense, a type can have a discriminant, which is a kind of parameter. And the data structure, the shape of the data structure will depend on the value of the parameter that's called the discriminant. So here I have an example. I have a student record. So each student has a major, letters, science or technology. Grades are that the French grading system from 0 to 20. And everybody has a name and a grade in English, in math. And depending on the major, it will include a grade in Latin or physics and chemistry or technology or something like that. So it's a bit like having a union in a struct, but it's fully controlled. You can, if your major is in letters, you cannot access a node in a grade in physics, okay? Because it's really a variable shape data. Okay. Object-oriented programming is a typical example of building blocks. So we've seen that packages support encapsulation, limitation of visibility. There are a special kind of types called tag types that support dynamic dispatching. So a class is an encapsulation of types with dynamic dispatching. So it's a programming pattern where you have a tag type declared in a package. So a typical example, a widget, not very original. You define a tag type, so that's a naming convention, you can call it instance, and you give the name of the class to the package. So you would write widget.instance if you want an instance of the class widget. Okay? And you declare operations, so it's called a primitive operation in Ada. It's a method, if you want, in all the operations on your instance declared in the same package. And then you can derive a new type from an existing one, adding some new components and redefine operations, so that's the usual way of doing object orientation. I didn't talk about pointers. There is no need to have pointers when you need object orientation. Ada, since 1983, has always been able to allocate variables of dynamic size on the stack. Why do all the languages need pointers as soon as it comes to object orientation? Well, some people hide that under beautiful theoretical concerns. But the real reason is as soon as you don't do object orientation, you have polymorphism, so you don't know the size of the objects, and so you cannot declare them on the stack. But in Ada we have dynamically sized objects, so we have no reason to be in any way connected to pointers. In practice, of course, you often need pointers to objects because you have lists of objects or things like that. But you need pointers because you have lists, not because you have objects. Okay. And something that's also very special to Ada is that we make the difference between a node in a tree. I'm talking about a hierarchy of types, okay, that defines a tree. And because we are very strongly typed, a specific type is just that type. And we have what we called, so here I have widget, window, menu, a pop-up window, and, well, why do I have two arrows here? That's an arrow. And a scroll down menu and so on. That makes a tree. Okay? An object declared of type widget can hold only values of type widget, nothing else. And we make the difference with the whole tree. A node in a tree generates a tree. So it's a different type in Ada called widget class, which is in a sense the union, the union of all the values from widget and all types that inherit from widget. And so we make a clear difference between a node and the tree that's generated by that node. So that's also something quite original. It has a number of implications. Well, I won't have time to discuss everything here. But it's certainly very interesting, and well, it brings something new to the object orientation to have that distinction. And so I can, for example, have a procedure move that applies equally to any widget, so its parameter is type widget class, so it means it can accept any value in the tree, so it can be a window, a menu, a pop-up, whatever you want. Okay. And well, you can use it normally, and since 2005 it's the same trick as in Python, for example. The first parameter can go in front if you want the object.method notation. Okay. Interfaces were added to that in 2005, so you can derive from one type and several interfaces. Just a small improvement, or an interface has only abstract methods or null methods. we have methods that do nothing. You have no diamond problem because they are all equivalent. And so I can have a persistent type. It's something that offers read and write. Okay? These are more convenient functions. So, but exceptions, the only thing important is to note that everything that can happen at runtime generates an exception. In C++, for example, exceptions were added quite late in the history of the language. And there is also that idea that the compiler should not do something that's not written by the programmer. I understand that position. It's not the Ada's position, that's all. So in Ada, our position is that if anything goes wrong, the program has to be aware of that. So in C++, if you have an overflow, nobody knows what happens. Okay, it's not defined by the standard. In Ada, an exception is raised because the exceptions are built into the language, and anything bad that happens generates an exception. Every exception can be handled, because if you are writing software for a missile, for example, you don't run after it to hit Control-Alt-Del, okay? The software has to take care of anything. And that's an old proverb, so once you've taken care of the unexpected, remember to take care of the unexpected. Generics, time is running, so I'll go faster, is a way to have, it's like templates in a sense, to reuse algorithms that can work on any type. So this is to swap two variables, it's generic from private type, and from this model, in a sense, you can instantiate a real procedure by providing the type. Tasking is built into the language, so threads, they are high-level objects that can be passed to subprograms and things like that. We have ways of communicating, high-level communication through rendezvous that are between tasks and protected objects. And so I don't have time to give the details, but tasking is easy to use. That's important. You just declare a task object and you have your task. It starts and finishes as appropriate. And in general, people use pthread only when forced to. While in Ada we have such a convenient tasking model that, well, if we can use tasking, we do. It's just not more difficult than anything else. I'd like to show you this because it's important. Here, how do we access the low level from a high level approach? First, imagine this represents some hardware register or something like that. Okay? I give a description as a record, like a struct if you want. And then you can have what is called a representation clause that will tell you bit by bit where the various components are. So this syntax means that on that boolean is bit 0, that count is bits 1 to 7, and status bits 8 to 15, exactly at a bit. And then you still use the high-level statements, indexing, that's an array, and that's all. And at the lowest level, you get exactly the machine you want. So some people say, well, I need a low-level language because I have to make low-level access. In Ada, we say, you describe the low level, therefore you can keep a high-level approach and get what you want at the low level. Well, that is how to access bare memory. Time is running. There are features to include machine code. There are features to handle interrupts. It's really possible. You will have example later today. You have really ways to access the low level. The only thing in Ada is that it's not forbidden to do low-level programming, but you have to state it clearly. If you want to use these things, somewhere you'll say that you depend on interrupt or that you depend on things that allow to somehow time circumvent the typing system. I gave you a small idea on annexes. So for system programming, real-time distributed system, a very interesting model would be worth several hours in itself. Information systems and numerics, and of course safety and security. Ada is really portable, which means it's really the same code. All these auto make and so on are ways to patch according to the variation. It's not portability, okay? And there is a validation suite to ensure that all compilers compile exactly the same language. And believe me, I have a number of programs. I never have different versions between Linux, Windows, or whatever. It's 100% same code. Well, okay, to be honest, sometimes you need one package that will include, if you have explicit dependencies on the system. But that would be confined to one package. Ease of writing is also important, and we have, since the compiler has much information, we are lucky to be able to have compilers that give very good error messages, and that saves a lot of time. Like fixing, if you misspell one of your own variables, the compiler can tell, oh, there is a variable that's almost the same, maybe you wanted this one, and so on. Well, saves a lot of time. Of course, as I said, you are protected from many mistakes. Strong typing, in the first time you try it, you are angry at the compiler. Why does that damn compiler don't accept that? And then you realize, oh, I made a mistake. Thank you, gentle compiler. So, you spend your time on designing. That's better you than chasing bugs. It can interface with other languages. It has also a number of things that are unique to Ada. So you can expect at that time that I tell you, oh, you should use Ada. I won't tell you that. You are grown-ups. You are nice people. You are able to know what you have to do, okay? Now, what I want just to tell you is please try Ada. See how it works. You have free compilers, free for downloading. Use it. You have a community that is willing to help you in the first step, and then you can judge for yourself. Thank you. Questions? Yeah?
When you were talking about loops, you mentioned that some projects can be formed with loops. Is there an integration with some similar improver and some similar?
So, yes, and there is even a subset of Ada, which is at the same time a kind of a superset, because there are some extensions in the form, well, I won't be into detail, called Spark. And that's a formally provable part of Ada with tools. Do we have something about Spark?
Presentation about Spark this afternoon at 3 o'clock in this lab room.
So you'll be interested in that. Thank you.
Thank you.